for our last talk of the day. It's a pleasure to introduce you Michele Graffeo from SISSA, Italy, who will talk about double-nested Hilbert schemes of points on smooth curves. Thank you, Michele.
Thank you. So thank you for the introduction and thank you for the invitation. So Rio is fantastic, the conference is fantastic, and IMPA as well. So thank you for the invitation. So today we talk about a project which is joint with, probably at some point you will see better, bigger. So it's joint with Lella, Monavari, Ricolfi, and San Martano. And I will talk about this double-nested Hilbert scheme, which was introduced by Monavari in 2022. And then together with this co-author, we studied the geometry of this object. Of course, I think that all of you know what a smooth curve is, so I will focus on the first part of the title, and I will first try to explain what the double-nested Hilbert scheme is. So I will start in the opposite way. So I will start from Hilbert scheme, and then nested, and then double-nested at the end. Okay, so the story starts with Grothendieck, and as usually when you want to define a moduli space, you start from a functor, and then you prove representability. So the first definition is the definition of Hilbert functor of point. So what you need is X to be a quasi-projective variety. And at some point I will focus on smooth varieties, because not all the results I'm going to mention are true for any varieties. So let me do it now. So smooth. So again, this is not needed for the definition, but today I will stick in the smooth word. And then you need a natural number. Okay, given this data, you define the Hilbert functor of n points in this way. So it is a functor, n point on X. And it goes from the opposite category of scheme over C. So I take the occasion to say that I will work over C to the category of sets. And this associated to any base scheme B, a set which is the set of families parameterized by B. What does it mean? So I'm considering closed subschemes of the product, X times, so maybe it's better B times X, such that, so you require a reasonable thing for this to be a family. So you want this to be B flat, B finite, of B length, I'm going to explain, B length n. So what does it mean, B flat, B finite, and B length? So all of these are properties which are properties relative to B. So you consider the canonical projection from the product to B, you restrict the projection to Z, and you ask this projection to be flat, finite, and once you are flat and finite, then all the fibers have the same length, and you require this length to be n. Okay? And the result by Grothendieck, so also the definition is by Grothendieck, but the result by Grothendieck is that Hilb n X is represented by a quasi-projective scheme, which I will denote by, yes, let me write it here, X n, to distinguish it from the Hilbert functors, to not make confusion with the definitions, with the notation. So what does it mean that it is represented? If you don't know about this terminology, just remark Xn is the, let me put this in bracket because I don't really want to define what fine is the moduli space of zero-dimensional closed and finite subschemes of X of length n. So in few words, this means, so fine means more than what I'm going to say, but this means that the points of Xn are canonically in bijection with these objects here. So zero-dimensional closed subschemes of X of length n. Actually, being a fine moduli space means more, but I will just focus on this description. So before to go, so this is the Hilbert scheme. It's a classic. I won't spend more time on this. This is very classical. I hope that many of you have already seen this object. And another object that I want to define is the Hilbert set of points, which is just the union of the closed point of this xn here. So I define Hilbert points of x to be the disjoint union for n greater or equal than 0 of xn, and I put here C to record that I'm just considering the closed points of this scheme. So why do we like this set? Because this actually admits a poset structure. So this is a poset. Why is it a poset? Because as I told you, all of these sets here correspond bijectively to closed subschemes of X. So given 2 points, these 2 points will correspond to 2 schemes, and you will say that a point is smaller or equal than another point if the corresponding schemes are contained one in another. So if you have a point Z, so Zi in Hilbert points of X for I equal to 1 and 2, you say that Z1 is smaller or equal than Z2 if Z1 is contained, enclosed of course, in Z2. In Z2. Okay, this is a scheme and this is just a set. And we will see that this viewpoint will be very helpful later. So this is the Hilbert scheme, and now I want to generalize this to the nested situation. Again, you do something similar. So now you define, for the I will define the last functor now, definition. So here the data are a quasi-projective variety and a natural number, and what I'm going to do is to substitute this natural number with a non-decreasing sequence of natural numbers. So x as before, and then I take 0 smaller or equal than n1, smaller or equal than n2, smaller or equal than n to the r, and I will denote this with an overbar. There will be an n underlined, so this is just overbar, and you define the nested Hilbert functor of point, Hilbert n of x, to be a functor, again from the same between the same categories, and you associate it to any base scheme B. Now here you have here you have just one family, and now you take collection of families closed inside Z2 R such that, so inside X such that Zi is B flat, B finite, and of B length and I. Again, the result this time by Klepp that this functor is representable. So Hilbert n x is represented by a quasi-projective scheme x n. And again, the meaning is the same. So a point here is just a sequence of scheme. So the remark xn parameterizes sequences Z1 inside Z2, ZR, such that Zi is closed in X and, sorry, in X times B here, pardon, is closed in X, and the length of Zi is Ni. So in order to further generalize these to higher dimension, I will give a different description of these objects, but first let me give you just a flavor of the difficulties in understanding the geometry of these schemes. And I will say something about the classical Hilbert scheme, just to let you know that some fact. xn, so the classical Hilbert scheme is smooth if and only if the dimension of x is equal to 2 or n is smaller or equal than 3. So this is almost always singular. And for instance, about if you are an algebraic geometer, for instance, you want to know, or a geometry in general, you want to know the irreducible component, you know that xn is irreducible. So let me say differently. If the dimension of x is smaller or equal than 2, then xn is irreducible. While if the dimension of x is greater or equal than 4, then xn is irreducible if and only if n is smaller or equal than 7. And as you can see, I left the case dimension of x equal to 3 because this is the most challenging dimension. Because in dimension of x equal to 3, we know that if is irreducible if n is smaller or equal than 11, and reducible if n is greater or equal than 78, and nothing is known in the middle. So nobody knows when these Hilbert schemes start to be reducible. Okay, so this is very hard to understand the geometry of Hilbert schemes already in the classical setting. And for instance, just to mention in word that if you go in the nested setting, the Hilbert schemes start to be reducible already in dimension 2, and we will see that this happens in dimension 1 for the double nested situation. Okay, let me start trying to introduce the double nested Hilbert scheme. And to do this, I will change viewpoint, and I will define again the objects that are parameterized by the nested Hilbert scheme. So, definition, nested, let's say n nested scheme is a non-decreasing function z, let me write it here, z from the set 1, sorry, it's too small here, sorry, z from the set 1 R to Hilb points of x such that the following diagram commute. So let me explain what's going on here. When you have a sequence, this is something for undergraduate students, when you have a sequence, you can interpret the sequence as a non-decreasing, as a function from some set 1R to the natural numbers. In this case, I'm looking for non-decreasing, to non-decreasing functions. On the other hand, I have the length, so to each point here I can associate its length. And again, this is a non-decreasing function. So what I'm asking here is to have an association. I want to associate to each number from 1 to R schemes with the property that each of them has the correct length. So this definition here is precisely this description here. Okay, is this clear? Okay, so the idea behind the double nested Hilbert scheme is to substitute this totally ordered set with some posets, finite poset. And today I will talk about the situation in which the poset is a Young diagram, and this will give a double nested Hilbert scheme. While if you consider general posets, you will find something that is an ongoing project with the same co-authors, so you will find something that we will call the poset Hilbert scheme. And I will say something, but the situation is going to be much more pathological in that case. Okay, if there are no questions, I can move to the proper definition of double nested Hilbert scheme. Yes? Is smooth if and only if the dimension of x is 2 or the number of... Huh? Sorry, smaller or equal, thank you. Yes, thank you. Yes, I've written smaller or equal there, but not here. Thank you. This is always connected, so in the two cases, okay. So the idea here, where is the... So idea is to use Young diagrams, and you get the double-nested Hilbert scheme, or posets in general. And you get the poset nested Hilbert scheme. Okay, but in order to do this, I have to say what a Young diagram is, so it will need some effort, but we will go in that direction. So some convention. So first of all, I will endow the natural plane of a poset structure, which is just the component-wise comparison. So I will say that a pair AB is smaller or equal than a pair A prime B prime if A is smaller or equal than A prime and B is smaller or equal than B prime. The other thing that I want to just write this in this side of the blackboard, this is the orientation that I will adopt to make pictures. So that's the A axis and this is the B axis. And in this situation, what is a Young diagram? So lambda inside N2 is a Young diagram. I will, for brevity, write a Young diagram in this way if it is closed under smaller or equal. I will make a picture to explain what I want to say, but let me just finish to introduce the objects I want to introduce. So this is a Young diagram, and then I will say that the circle of a Young diagram is just the set of maxima, which is not unique because this is just a poset of lambda. And while the subcircle, of course I will make a picture to describe, but let me just write the definition, is the set of boxes in lambda, and I take the occasion to tell you that I will denote points in the natural plane as boxes, just to underline the discrete nature of the natural plane, and also because this will be very, I mean, it's better to adopt this notation. You will see in a second why. So it's the set of boxes in lambda such that box plus 0, 1 and box plus 1, 0 belongs to lambda, but box plus 1, 1 does not. Now I'll draw a picture to explain. Let me copy the picture because for some reason I've chosen this, so it's something like this. Okay, this is a Young diagram, meaning that if a box belongs to the Young diagram, then all the boxes above and all the boxes on the left belong to the Young diagram as well. So this means to be closed under this order relation. And then what is the circle and what is the subcircle? So let me denote by cross the circle and by a circle the subcircle. So the circle is the set of maxima. So here is the circle. These boxes are greater or equal than, are not smaller than any other box. And the subcircle, let me draw it and then I will explain why is this. So you see, if I start from a circle, if I add 1, 0, I go here and I stay inside the Young diagram. If I add 0, 1, I go here. So I stay inside the Young diagram, while if I move using 1, 1, I go outside. And there are precisely two subcircle boxes. And this is a general principle. The subcircle has always cardinality 1 less with respect to the cardinality of the circle. And also notice that in dimension 2, these two sets are totally ordered. The order is not compatible, of course, with the order of N2, but you can start, for instance, from the right or from the left and read them one by one. So this will be very helpful when you want to do, for instance, induction. I mean, in dimension 2 and with the Young diagrams, the situation is much nicer than with a general poset. Okay, and the last piece of combinatorics that I need is the notion of reverse plane partition. So we have something here that substitutes the set 1 to the R there. So I want something now that substitutes the function n over bar. And so this is going to be a reverse plane partition. So definition, so let lambda be a Young diagram, a reverse plane partition of shape lambda is a non-decreasing function from n, so this is the underbar from lambda to n. Okay, and I will denote this set, so and I will say that n belongs to R P lambda. So let me make again a picture to explain what's going on. Actually, I will make 3 pictures, which are examples that will be relevant for us in the rest of the talk. So what I have to do is to associate to each box of the Young diagram a number in such a way that the numbers do not decrease along rows and columns. So example, and 1 will be through all the talk, and 1 will be this one, 0, 1, 1, 2, and 2 will be 0, 2, 2, 4, and n3 will be 0, 0, 3, 0, 2, 5, 3, 5, 5. For some reason, I have chosen these examples. So, and also all these examples are squares, but in general, as you can see, not all the Young diagrams have this shape, but these are relevant to us. You will see later on in the talk. Okay, and now you can define the analog of an n-nested scheme in a similar way. So definition, you take n reverse plane partition of shape lambda, then n configuration is a non-decreasing function z from lambda to the Hilbert set of points such that the following diagram commutes. So again, I have here the length, and what I put here, the only thing that I can put here, the reverse plane partition. Okay? Any question? So the construction really imitates the situation for the classical nested case. So this is the last. So what is the double nested Hilbert scheme is the moduli space of these objects. So I'm not going to write again a functor because it's the same thing. I will just write the definition, which is due to Monavari. At least his existence was proven by Monavari.
So when you say it's a non-decreasing function, is the function C?
Yes. Yes.
But how do you order it?
I explained this before. If you take, this is a poset. If you take 2 points, they correspond canonically to 2 schemes. So if there is a containment, then the 2 points are one smaller than the other. This is just the union of all the closed points. It's just a set. It's not a scheme. So it's just, I need this just to say that I need this just to define the, I mean, you can define this in a different way. It's just to underline the importance of the poset structure. So definition. I also say theorem because it must exist, so theorem by Monavari. So the double nested, and the n double nested Hilbert scheme of points on X is the moduli space of n configurations of X. Of course, I didn't write it, but it's a configuration of X. And let me make an example which relies on the first of these three reverse plane partition. So example, if you take n1, then I want to give you two examples of points, so z1 and z2. Of course, I will denote these, so I denoted, the notation is this one, the same as before. So I take 2 points inside here. And so let me give you two examples. So the first is the following. Z1 is, I take, so here I can only take the empty scheme, but here I have choices. So let me also fix for a second the dimension of X equal to 1, because then at the end I will focus on curves. And so what I do here is I take a point P, sorry, Q, let me use the same notation, just point P, P plus Q, and then I take Z2 to be empty set, P plus Q, where P and Q in X are distinct. Okay, this makes sense because I am on a curve, so on a smooth curve, so smooth points are Cartier divisors, so it makes sense to add them. So writing in this way, even though I'm working with the schemes, with zero-dimensional schemes, in this setting it makes sense to write this. So why am I showing this to you? Because this is the first example of reducible nested Hilbert scheme, and I will explain this also more in details later, but just to give you a flavor of the difficulty, the point is that what is the reasonable definition of isomorphism between two n configurations? So it's something that associates to corresponding schemes. So you give an isomorphism between corresponding schemes, so you would like to associate this to this, P to Q, P to P, and P plus Q to P plus Q in such a way that all possible diagrams that have to commute. So you can understand this as a square. You can understand this as a square, and this is another square. And so what you want to do is you make a cube of commutative diagrams. So of course, Q is isomorphic to P, and P is isomorphic to P, and P plus Q is isomorphic to P plus Q. But the point is that you won't be able to make this diagram to commute if you write the unique possible isomorphism that you have. Because these P and this Q are different, so you are not going to be able to make the diagrams commute. And also, if you perturb a bit, for instance, P, you don't change isomorphism classes. So if you consider the schemes, I will write this properly later, but just to give you a flavor, if you consider the schemes which are isomorphic to Z1, these constitute an open. Same thing for Z2, and these two opens are disjoint. So this Hilbert scheme is reducible. It admits two irreducible components. We will see this in details later. Okay? This is just to give an example of the difficulties that you find when you start working with these objects. Okay, before to start studying the geometry of Hilbert schemes, what we need is to understand the algebra behind the reverse plane partitions. Of course, so let me write these some facts about reverse plane partitions. So, remark that reverse plane partition of a fixed shape together with the sum is a cancellative monoid. This just means monoid. This means that it makes sense to sum two functions, because if you have two non-decreasing functions, the sum will be a non-decreasing function. Cancellative means that a plus b equal to a plus c implies b equal to c. So this set here has an algebraic structure, and we will need to understand it in order to describe the geometry of the double-nested Hilbert scheme. I will say Hilbert scheme to be faster, but I will always mean double-nested Hilbert schemes. So definition, A subset of the natural plane is connected if for any decomposition as a disjoint union there exist two boxes sharing an edge. This just means that you have two boxes which are one on the, two near boxes. So this is the reasonable definition of connectedness. So this is the first definition, and then a subset of a Young diagram is an upper set if the complement is a Young diagram. And finally, an indicator of shape lambda, and I will write it nu in ind lambda, is the characteristic function of a connected upper set. So what do I mean? I mean that, let's say upper set U. I mean that nu is a function from lambda to the natural numbers associating to a box 1 if the box belongs to U and 0 otherwise. Okay. These objects are the building blocks of the reverse plane partition, as I'm going to state in a second. So let me write. Of course, stop me if you have questions, but probably it's better first to say why these objects are important. So, fact. Okay, I don't need it. So, fact. The first fact is that in lambda is probably better to give an example before to give the fact. Yes, let me give an example. Example. Let me fix lambda to be our favorite Young diagram. So I want to list all the possible, and now I need the paper because I want them to be presented in a special order. So I want to list all the possible indicators. Of course, the Young diagram is a finite set, so it has finitely many subsets, and so finitely many indicators. So I can list them. So the indicators of shape lambda are the following. So the first is this. So the first in my choice, there is no order. 0, 0, 1, 1, 0, 1, 1, 1, and 0, 0, 0, 1, 1, 1, 1, 1. And let me call this nu1, nu2, nu3, nu4, and nu5. So as you can see, the complement of the upper set, of which each of them is the characteristic function, is a Young diagram. So it is where you see the zeros. This is a Young diagram, Young diagram, Young diagram, and the empty Young diagram if you want. So these are the possible indicators for this reverse plane partition. And so fact, yes. As you can see from here, indicators are non-decreasing functions. So in lambda is contained in RPP lambda, but more than just contained. In the lambda is the unique minimal set of generators of RPP lambda as a monoid. So every element inside this set, inside this monoid, can be written as a linear combination of indicators with natural coefficients. But I've never said in a unique way, and indeed it's not true. You can have different way to write down a reverse plane partition as a sum of indicators. And so we need a definition of factorization. So definition, we take a reverse plane partition of shape lambda. So what is a factorization? A factorization of n, let me write it t inside fact n, is a sequence n no for no in lambda. So this is an element in n to the in the lambda, such that n equal to the sum of n no. So I should put here underline, but I will forget later. So I'm saying that a factorization is just a bunch of numbers such that if I sum all the indicators and I weight the sum using these fixed numbers here, I recover the original reverse plane partition. So it's a way to write the reverse plane partition in terms of the generators. Okay? So the factorizations are not unique, and this is going to be very important later on in a second. And, but a very important invariant attached to the reverse plane partition is the following number. So definition, the length of t is just the sum over nu in the lambda of n nu. And before to ask if there are questions, I want to immediately say that the proposition for every t and t prime factorization of n, the length of t equals the length of t prime. So this is not an invariant of the factorization, but this is actually an invariant of the reverse plane partition. And so I will denote this number by omega n, and we will see how important is this invariant to describe the geometry of the Hilbert scheme. The important feature, this invariant is so important that I want to explain a different way to compute it, and so proposition that omega n equals to the sum for all boxes, for all boxes in the circle of lambda of the reverse plane partition computed in the box minus this. I'm going to give an example, of course, the subcircle of lambda of n computed in the box. So let me give an example to explain what do I mean here. And so I can compute, for instance, omega for n1. For n1, n2, and n3, there was no subcircle. So you just look at the circle. So this part is 0. And so you can immediately say that this is 2, omega n2 is 4, and omega n3 is 5. But for instance, you can look to something more bit more intricate. So what do I choose here? 6, 3, 1. And so this number is just, we have 2 circle boxes and 1 subcircle box. So it's 6 plus 3, this part, minus 1. So this is 8. Okay? This is a very important number, as we will see in a second. Okay. Just an example to show you something about this factorization. So example. The first example is that I can take 0, 1, 1, 2, and I can write it in 2 different ways. 0, 0, 1, 1 plus 0, 0, 1, 1. So this was nu 1 and this was nu 2. Or I can write it in this different way. 0, 1, 1, 1. This was nu 3 plus 0, 0, 0, 1. So there are two different factorizations. Both of them have length 2, as expected, and we can factorize this reverse plane partition in two different ways. But if I take twice this reverse plane partition, I have, of course, twice its factorizations, but I have also something more, the sum of the two. I can write this as 2 nu 1 plus 2 nu 2 or 2 nu 3 plus 2 nu 4, but I can also write it nu 1 plus nu 2 plus nu 3 plus nu 4. So as you can see, the length is always 4, as expected, it's written here. But we have three different factorizations, and this will be relevant later. So we are now ready to talk about the main part of the talk, which is the geometry of C. And so now C is a smooth curve, so we will focus in the situation we care about. Okay. So the first thing I want to show you is a very easy way to deform, so it's something that I have already said, but a very easy way to deform n configurations. So suppose that you take a point inside the double nested Hilbert scheme, then you can define a family parameterized by the curve itself that deforms Z. You just need to fix a point, okay? And you define a closed, and I want to define some Z, which is equal to Z box for box in lambda. So remember that a configuration is a set, so a family is a set of families parameterized by, indexed by the boxes of lambda, and I want each of these families to be contained in C plus C. So I want a family which is parameterized by C. And I build the family in this way. I say that Z box equals to the trivial family if P does not belong to the support of Z. Yes, Z is. Remember that such an object is, again, a collection of schemes. If P does not belong to the support of Z box. Or to describe the family in this setting, I just tell you the fibers over each point of the curve. So this is the point Q, comma, Z box minus P plus Q. Otherwise. So in order to understand what's written here, just let me say something. So the point is that, let me give an example maybe to explain this. I take empty set inside A, inside P is the same as before, but I'm just changing a name, P plus A. So what I'm saying is that if, for instance, what I do in this, at this box level, here P does not belong to the support of this scheme, so I don't do anything. While here P belongs to the support of the scheme, so what I do is I just move P. So this is what I'm doing here. Over the point Q of the family, I find the point Q instead of the point P. I remove the point P and I put the point Q. Of course, there is a more intrinsic way to define a family, but I think that set theoretically is enough for the purpose of today, because I just want you to notice that this is enough to prove connectedness of this scheme. Theorem, or let's say proposition, Cn is connected. So why is connected? Because proof every Z is connected to n box times p for box in lambda. So what's this? This is just the configuration when you have n0, 0 times p contained in n1, 0 times p. Because what I do is just I take every point in the support and I translate it to a fixed point, so where p is a point in the curve. Okay, this is not so hard. I mean, this is kind of easy. So, but why do we care about the number that I've presented you before? Because actually, this is a topological property, but we are geometers, so maybe we want to know more about this scheme. So, theorem, the dimension of this scheme here is omega n. So how do we prove this? So the idea is that to construct a finite morphism over something known. So we proceed by induction. So induction over the cardinal M, which is the cardinality of the socle. Of course, I will not explain all the details of the proof, but just the case m equal to 1 and m equal to 2. I think that you can figure out how to do the inductive step. So the case equal to 1, I have something like this. I have just one Socle box. So the shape of the Young diagram is a rectangle. So let me say that I have the letter A here. And of course, I have a finite morphism over the classical Hilbert scheme. Why? Because this is a finite subscheme of a curve. So there are, if you fix a scheme here in the Socle, corresponding to the Socle boxes, there are just finitely many ways to fill the rest of the table. Therefore, this morphism is finite. So these two objects have the same dimension. But we know the dimension of this guy is A. So this has dimension A. And you see, I've written some times ago how to compute the number omega n, but this is precisely omega n. Because it's the sum over all the Socle boxes of the entries and minus the sum over the sub-Socle boxes. But there is no sub-Socle here. While for m equal to 2, what we do is the following. In this case, the shape is something like this. I have A, B, B prime, and C. So the first thing that I can do is I can get rid of the first columns but the last, because again we have a finite morphism. So this is finite. And also we have a finite morphism over B, B prime, C, and A. But now, once we fill the first rectangle, we are almost free to fill the remaining part, the tail. So what I'm saying is that this is isomorphic, let me write it bigger, to C of B prime minus B, C minus B, times, so C A. And again, by the previous step, so we are completely free. So once we put B points here, we have just to put B prime minus B point here, and so on. And we are completely free to do this. So this is just a product. And so now, by the previous step, the dimension of this guy, so the dimension is C minus B plus A. And C and A are the entries of the Socle, while B is the entry of the sub-Socle. So again, this is omega n. Okay? You can imagine the inductive, how the inductive step works. Are there questions? So the third property that one would like to investigate is the behavior of the irreducible component. So I told you at the beginning that these objects are almost always reducible. So let me say something about it. So irreducible component. So the example as before is the following. I define Wi to be the set of points Z in here, 1, because I'm taking the example of before, such that Z is isomorphic to Z1. And then I take the closure. So now, what's the point here? As we saw, so this is for I equal to 1 and 2. So remember, we had just 2 points involved, P and Q. So 2 degrees of freedom. I think you can believe me that Wi has dimension 2. But now we know that the Hilbert scheme has dimension 2. So of course these 2 are irreducible components. And what is the point here? The point is that you can write Z1 as nu 1 plus so times P plus nu 2 times Q. So remember that, just to remember you, this was empty inside Q, inside P plus Q, inside P, inside here, while you can write Z2 as nu 3 times P plus nu 4 times Q. But look, nu 1 plus nu 2. This is one possible, where it is? Yeah, this is one possible factorization. And nu 3 plus nu 4. This is the other possible factorization. So the statement is that the factorizations are in bijection with the irreducible components. And from this you get also equidimensionality. So let me write this properly. Yes. Theorem. So denote by sigma Cn to be the set of irreducible components of Cn. Then there is a bijection from fact n and sigma Cn. And second, the dimension of, so let me call this phi. The dimension of phi of t is omega n for every t in fact. So how to prove this? So for any t in fact n, so for every irreducible component. So how do you prove this? So you just one direction that will be important in a second. So what I do is the following. What do I do? Okay. So I take the factorization. No. So let me. A1 plus, to not use nu 1 because nu 1 was already used before. A omega n. So they are not necessarily all distinct. I'm just writing all of them. I know how much of them do I have, so omega n. And so what I do is I associate to this configuration, so to this factorization, the following irreducible component defined in this way. So AI pi such that pi are distinct. As you can see, again, you have, I know that this is just hand waving, but of course in the paper is more rigorous, the argument, but you have omega n degree of freedom to build this irreducible component, because you choose omega n distinct points, and so this locus here has the same dimension of the Hilbert scheme. So this is a component. The part that I'm not going to prove is the other side, but to conclude the talk, I really need just this direction. So is it clear? I'm just taking different points and I'm putting different points inside the Young diagram, and then the sum give me the generic point of the component, and then I take the closure. And of course, the dimension of the closure is the same as the dimension of the Hilbert scheme, of the locus that I'm describing. Also notice that everything here depends on n, does not depend on the curve. Because for curves, everything is just combinatoric here. Okay, so to conclude, the fact is that it seems that all the components are symmetric product of symmetric products of copies of the curve, no? Because I'm choosing freely some points, but if there is some repetition that I'm not really free, but it's not like that. So one can look this in this way. So if I take a factorization T, then I can do something like this. So I take the product for no in the indicators of C and no, and I can go to some component, and I do the following thing. I take P1 plus P and no. So what is an element here? Is an effective cycle of length n nu, and I take one effective cycle for each nu. So this is a typical element here, and what I do to find a point in the component, I just consider the weighted sum of these. So now the question is, so this I should do like this. And then I have to sum overall no. Okay. So now the question is, this is for sure a birational map. The two sides have the same dimension. Is this map an isomorphism? Notice that this map is also finite for the same reason I explained you before. So by Zariski main theorem, this map is in isomorphism if and only if it is injective with injective differential. So what I will do in these last 2 minutes is just to state the criterion to understand if the component is smooth or not. And if I do it in 1 minute, I'll also give an example. Otherwise, I will stop here. So theorem is the following. So take the component considered there. Then this is smooth if and only if there is a non-trivial relation, let me say Z relation, sum of M nu equal to 0, yes, where M nu different from 0 implies N nu different from 0, and if so, phi t is injective, is not injective, if and only if the modulus of M nu is smaller or equal than the modulus of N nu. for every no. Okay, I have 1 minute, so in this 1 minute I can explain how this theorem applies. So the first example is if I consider, where it is, here, 0, 2, 2, 4, I can write this in this way. Let me write it as no 1 plus no 2 plus no 3 plus no 4. But remember, we saw before that if I call this A and I call this B, then A is equal to B. So I have a relation here. A minus B is equal to 0. And this relation satisfies 1, but does not satisfy, and does not satisfy 2. So in this case, the map is not injective. While if I have the other example, so I can also show that it is not injective. Probably it's better to show that forget about the other example, but just let me conclude with the fact that this is not injective. C times 4 to Vt. I'm going to write explicitly this map. And so this map takes the point P, Q, R, S to empty set, P plus S, P plus R, and here I have P plus Q plus R plus S. But you can check that the point, so check that phi of P, P, R, R equals to phi of R, R, P, P. So this is not injective. While if you play a bit, you will see that in the other case, the map, for the other reverse plane partition that I gave you at the beginning, the map is injective, but the differential is not. So the two pathologies can occur, both the pathologies can occur. So yes, and I stop here. Thank you.